After this practice of solving quiz 1, remember during the online session some of you were requesting to get more practice and so on, and this was my answer, that we solve many very good problems during the classes already, and if you really understand them, then you can solve a lot of the other things yourself. On top of that, I have sent you the homework. So all of you who do the homework themselves, you see, the problem is you take life easy, some friend solves it and you just submit it. Then you are not really learning anything. You are submitting it, but the numbers for all the homeworks together will be very small, 1%, 2%, something like that. Why do I do that? The homework is basically there for you to learn, not to copy from somebody and submit it. So if you do all the homework problems also yourself, then you learn a lot. And then in the quizzes and exams, you are very strong. On top of that then, right, the examples that we solve during the lectures, then the homework problems, plus like this, that quiz is over, now I solve the quiz also with you. So like this, we will solve enough problems so that you have a good idea. But you are not school children of year 3 or year 4 in the school, that every time, every problem, you already know the solution, the teacher has done it with you, you just reproduce it. No, you are engineers and you are going to be doing a lot of independent work in the field. So we will solve some problems, and for some, you think and go back to your lectures and see what is the theory. So it is not that every problem that comes into the quiz, a very similar problem has been solved by me earlier, right? That will make you very weak engineers. So we will see. So now let us get back to the lecture. The Hall-Pech equation, we told you last time, sigma y is the yield strength, sigma naught is a constant, k is a constant, and small d is the average grain diameter. So yield strength can be found if we find the average grain diameter of the metal by microscopy, by looking at it under the microscope, right? And these values, these two values are experimental values. They are different for each metal. And if we give a problem on this metal, then we will give these constants. Okay. So you see, this is inversely proportional. If this D was here, then they are directly proportional. So if D is increased, yield strength will increase. But what did we learn last time? That grain boundaries increase the strength of a metal. And if the grain size is small, if the material is fine grained, grain size is small, then there will be many more grains in the metal, and therefore the amount of grain boundaries will be much larger. So because grain boundaries increase the strength of the material, and because in fine grain size, a small grain diameter, the grain boundaries are large, very many, therefore fine grain size increases the strength of the metal. This is what we found experimentally, practically, and here this equation tells you the same thing. If D becomes small, if anything, you see, mathematically, if anything in the denominator becomes small, the whole number becomes larger. So the smaller the grain size, the larger the whole value. So yield strength will be higher if grain size goes down, right? So this is, and of course, we have told you that strength and hardness go together. So if grain size decreases, strength goes up and hardness also goes up. Okay. Here we are showing you some copper, normal materials, copper, titanium, mild steel, nickel, aluminum alloy, that what are the values of these constants, sigma naught and the constant k, right? So if we give you any problem, then if these are the metals, then you know the constants. And if it is any other metal than this, then we will give you the values. I have told you that, you see, I sent you a formula sheet before the quiz. I will do that again before every exam and so on. By the time we cover the course, the formula sheet will be for all the chapters that we have covered. So you do not have to memorize any formulas, any equations. You should know the subject, you should understand it. And if you are working with me, what is So the solution, right? What is the Hall-Page equation? This is the Hall-Page equation, right? So put the first two values. You see, this is the grains dia. So put the grain dia number here and the stress yield strength here. So you have one equation, right? Equation 1. Then take this next one, this dia and this strength. This dia and this strength. You have equation number 2. So now you have two equations and two unknowns. You have two equations and two unknowns. Of course, what you do here is you have to square, right? First, take the sigma naught there. Sigma y is some number. Say it is 25 upon sigma naught. And then square it. Once you square it, then the root sign will be gone. So from the first equation, from the second equation, solve them together. There are two equations and two constants. So if you, for example, this is equation 1, that is equation 2, this minus this, sigma naught will go away and you have only k left there and so on, right? So put the value there and solve it. Then you find the sigma naught and the k value. Then the third time, use the same equation, but this time you already know sigma naught and you know k, and the yield strength is 205. So find the unknown D, right? So I am not showing you the solution, but I am showing you the method. So sometimes we can do that so that you understand how to do this. But this was, I think, even before I did the solution. If you have practiced it on your page, then yes, you would understand that there are two unknown constants which we have not given in the question, but we have given three different sets of values. First, we have given an average dia and a yield strength. So you put into the equation and you say this is equation 1. Second, we have given another average grain dia and the yield strength. You put it into the Hall-Page equation, you say it is equation 2. So now you solve those two equations simultaneously and you find the two unknown constants. So now sigma naught and k are known. Therefore, now you can solve for any strength or any dia. Okay, good. We now continue with effect of plastic deformation, but now effect of plastic deformation on grains. On grains, not effect of plastic deformation on a strength, right? So on grains. So we have already told you that plastic deformation means dislocations move along a particular slip plane. Dislocations cannot go directly from one grain into the another in a straight line, because slip lines change directions at grain boundaries, right? The dislocation is moving like this. When it hits the grain boundary, it stops. It cannot cross over into the other. So it may change shape. As the number of grains increases, dislocations within each grain can travel a smaller distance before their movement is stopped by the grain boundary. Therefore, higher strength for fine-grained materials. If fine-grained material is there, lots of grain boundaries are there, it has higher strength. So let us see the figure. Now this is a microscopic figure. I told you that we have not done the chapter on crystal structure yet, but this is what, right? If you see, this is one grain, boundary is there. This one is one grain. This one is one grain. So when materials form, when we melt the metal and allowed it to cool it, then there will be a small crystal here, there will be a small crystal here, there will be a small crystal here, there will be a small crystal here. And as we keep on cooling, the small crystal becomes more and more solid. It is all liquid, it is becoming more and more solid. That crystal is also becoming more and more solid. This is becoming more and more solid. So they all start to grow on all sides, and ultimately this one hits this one. So this becomes the grain boundary. This one hits this one. So this becomes the grain boundary. This one hits this one. So this becomes the grain boundary, right? So crystals, initially the metal is liquid, and when we start to solidify it, small crystals form at different locations. Those small crystals are solid. They start to grow. The solid amount starts to grow, and ultimately all these crystals hit each other and these grain boundaries are formed, right? So this is what is there. So if there is any dislocation somewhere, if there is any dislocation, it can move in this direction until it hits. Once it hits it, it will stop here. Now it will have to change direction along the grain boundary if it has to move, otherwise it will not move. So lots of grain boundaries means lots of strength of the metal. Here they are showing exactly that, you see, this is a grain boundary and there were some dislocations. So this is now a much higher resolution microscope where even dislocations, you can see 0.5 micrometer. This is no ordinary microscope. Even a very good microscope, normal good microscope, very good microscope, which can enlarge to 500 times, will not go to micrometer level. We will study later on that there are special microscopes which can go to this. So, but if our microscope is this type where very small sizes can be seen, then we can see these dislocations. So these dislocations are moving, but they hit the grain boundary, they pile up. So dislocation pile up happens, and this means that the material is even more stronger than before. And if you see 20,000 magnification, this X means how much magnification there, 20,000 times. So normal camera, normal photograph, this is 20,000 bigger than that. Therefore you can see very small things inside. We are continuing with effect of plastic deformation on grains. One effect is that grain shape changes with plastic deformation. Now we are not talking of strength. What happens to the grain? You just saw some grains there. So when we do a large plastic deformation, then the shape of the grain may change. The shape of the grain may change. We will show you in the next figure. We will show you in the next figure that some shearing of the grains. You know that when we apply forces, then there are normal forces, tensile forces, and there are shear forces. So if the forces are parallel to the surface, we call them shear. So some shearing of the grains happens, and if we have an operation called rolling, then grains elongate, their size becomes larger in length along the rolling direction. You know, I mean, you may not have done manufacturing, but you know in many places rollers are there, and if you put a metal through two rollers which are rolling, then the metal will reduce in thickness and will become longer in length. So this is a very general method for reducing the thickness and increasing the area. So if the operation of rolling is going on, then in the direction where they roll, length will elongate. So this is one change, that grain shape changes. Second change that happens with plastic deformation, dislocation arrangement changes. Dislocation, we told you, we showed you just in the previous figure that some dislocation is there, it starts to move, and when it hits a grain boundary, it stops. So dislocation arrangement has already changed. A dislocation, a flaw was in some other place, it has moved, and with more deformation another dislocation moves, right? So we are showing you in the figure. So here we are just saying that there is a metal which has this grain structure, and after we put this metal through a roller, a round thing here and a round thing here, and the metal is rolled through it, then you can see that all of these grains are slightly longer in shape now. All of these grains has elongated a little. So right, so this is what we are showing you. Let us show more. This is now a huge magnification, 30,000 magnification. This is a machine called transmission electron microscope, very costly. But we are showing you a very close up that if this grain was about this size, this grain has elongated. So for now, I am not making you a champion of reading microscopic figures. We are just showing you as an example that when we do plastic deformation, then the grain shape changes and the dislocation movement or dislocation arrangement changes. That's what we are just showing you. We'll show you more figures, don't worry.